Hello everyone, welcome to lecture 57 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on metamaterials fabrication techniques. So, in this lecture we will first have a look at the metamaterial fabrication workflow for microwave metamaterials, which are basically done in printed circuit board or PCB form, and the length scale is typically millimeter scale. And then we will look into the optical metamaterials, okay, which are basically submicron or nanometer scale. Then we will discuss some common steps in metamaterial fabrication, such as substrate preparation, thin film deposition, including methods such as physical methods and chemical methods. So, first let us look into the microwave metamaterials fabrication workflow. So, it starts with the design and simulation. So, you design a unit cell and you set the period p, which is typically less than lambda by 2, okay, for an array structure, and then you can simulate this design in CST, that is computer simulation technology. These are commercial tools, okay, HFSS or COMSOL multiphysics. Okay. So, these are basically commercial solvers based on FIT, FDTD, FEM, different methods could be utilized. Okay. So, you can basically use them to solve the Maxwell's equations and finally optimize your design and obtain the parameters such as effective permittivity, effective permeability, and also effective refractive index. Okay. After that, once the design is finalized, you can go for the substrate preparation. So, you can select FR4, it is flame redundant 4, okay, Rogers, Taconic, okay, laminate, this could be used as substrate, and then you got to clean the substrate using acetone and then IPA, that is isopropyl alcohol, and then deionized water, and then dry it. Okay, you can also use oxygen plasma for that and then clean it. So, this is the cleaning part of the substrate. Now, you got to do the metallization if your substrate is already not copper clad. So, in that case you have to deposit the copper or aluminum. So, typically the thickness of the layer should be more than 3 times the skin depth. Okay. So, that can be done by sputtering or evaporation method, and you also need a thin adhesion layer made of titanium or chromium, okay, if needed. Now, when I say copper clad, okay, copper clad basically means that the substrate already comes with a copper foil laminated on it, either on one side or on both sides. So, you can take example of standard PCB laminates like Rogers 5880 or FR4. Okay. Now, if your board is copper clad, so you do not need to do the metal deposition, and if your substrate of the board is not copper clad, means it is a bare say quartz or silicon or Rogers film or PET, etc., then you need to first create the metallic layer, and after that is done you do the patterning or lithography. So, there you apply the photoresist, okay, that is in the form of dry film or liquid, okay, using spin coating, and then expose it to UV light for developing. Okay. So, you can also use milling or inkjet or say 3D printing to form the patterns on the surface of the substrate. And after the patterning is done, the next step is etching or lift off. Okay. So, you can do the pattern transfer using wet etch. Okay. So, you can basically use copper, or like you can do the wet etching of the copper using ferric chloride, copper chloride, or aluminum persulfate, okay, or you can dry etch and then strip the resist and inspect for any undercut or overcut done on the wafer substrate. And next you can do, if it is required in your design, say stacking or integration. So, this is required if you have gone for any multi-layer structure. So, you need to first align the layers and bond them with some prepreg or adhesive. Okay. So, these are basically pre-impregnated laminates. Okay. And then you need to drill or plate vias, add bias lines, components into the structure. Okay. And finally, once the structure fabrication is complete, you can go for the characterization, where you can measure with VNA, that is a vector network analyzer, using SOLT, that is short open load through, or TRL, that is through reflect line kind of calibration, using waveguide or in free space. And finally, you can analyze the S parameters, that is scattering parameters, to retrieve the effective parameters or the metasurface transmission or reflection phase. Now, let us look into the similar kind of steps, but slightly different, that is in the fabrication workflow for optical or even terahertz metamaterials. So, they are typically submicron or nanometer scale. The optical ones are basically nanometer scale. So, here also the design and the simulation step basically is the first step. So, here you got to set a sub-wavelength period, that is your period is much lesser than the diffraction limit, and design the structure and optimize the metal dielectric thickness using numerical simulation software such as CST. Numerical is based on FDTD, as I was telling. COMSOL is based on FEM, finite element method. Okay. CST is FIT, finite integration time. These are different commercially available solvers for Maxwell's equation. You can use them to optimize your design. Once the design is finalized, you can go for substrate preparation. So, for fabrication, take quartz, glass, sapphire or high resistive silicon, okay, as substrate, and perform the solvent clean. Okay. You can use O2 plasma, oxygen plasma, okay, and polish it to control the roughness and flatness of the substrate. And then you can go for, once the substrate is ready, you can go for the deposition. So, you can deposit thin layers which are like 30 to 80 nanometer of metal, okay, such as gold, silver, aluminum, using evaporation or sputtering techniques. A thin adhesion layer, typically titanium or chromium, is placed underneath so that the metal sticks well. Okay. Atomic layer deposition can also be used for alumina kind of spacers, okay, and you can use CVD, that is chemical vapor deposition, for depositing graphene in case you have tunable structures. Next, you can think of resist patterning. Okay. So, for that you got to first apply resist materials like PMMA, that is polymethyl methacrylate, which is a positive resist, or you can think of HSQ, that is hydrogen silsesquioxane, okay, that is typically used in EBL as a negative resist. Okay. So, you can actually use both for electron beam lithography, okay, and the photoresist you can use for spin coating methods also. Okay. So, using spin coating method, you can use it for deep UV or stepper or nano imprint lithography. Okay. And for patterning, what you do, that is mainly for resist coating we have seen till now. For patterning, you can expose the resist using EBL or deep UV or nano imprint lithography, and then develop the patterns in chemicals to reveal the features. So, in that case, you have to perform a short oxygen DESCAM to remove the thin residue. Next is the method for etching and lift off. So, if using metal patterns, you dissolve resist in acetone. so only the pattern metals will remain, and this method is called the lift off. And after etching, for dielectric metasurfaces you can use reactive ion etching or RIE, or for sculpt structures you can use inductively coupled plasma. So, that is typically used for the dielectric metasurfaces. And then in the final step you clean and inspect to confirm the fidelity of such structures. So, stacking and integration becomes the next step if you have a multi-layer structure as discussed before. So, if you build a metal insulator metal kind of a stack or any other multi-layer design, so the alignment between the layers become very critical. So, here the functional integration, for that you got to add phase change materials like VO2, GST or graphene, okay, and apply passivation layers for protection, and also you got to add electrodes for external contact. And once the device design fabrication is complete, you go to the characterization step. There you can use UV visible NIR, FTIR, that is basically Fourier transform infrared spectroscopy. Okay. Sometimes you also go for angle resolved one, okay, to measure the transmittance, reflectance and absorption. You also do ellipsometry that can extract the film thickness and the refractive index. You also perform structural tests using scanning electron microscopy or AFM to measure the critical dimensions or surface roughness, and also that allows you to extract the effective parameters such as permittivity, permeability and refractive index from the measured data. So, now let us look into substrate preparation in details, which is basically a common step for both microwave and optical metamaterials fabrication. So, substrate preparation for metamaterial fabrication, as I mentioned, is a critical step. This is the first step towards fabricating metamaterials, as the quality of the substrate directly impacts the performance of the final device, and here are the key steps that are involved. First is the selection of the substrate. So, based on the frequency range you will be working on and the dielectric constant epsilon r, the loss tangent of the material, thickness and the mechanical stability, you got to choose which one of these is basically your suitable substrate. So, typically you have FR4, Rogers, quartz, silicon, glass, among them you choose. Next you do the substrate cutting. So, you basically cut the wafer or the board into the required size using dicing saw, laser cutter or precision mechanical tools, and you got to ensure that the edges are smooth to avoid cracking during deposition or lithography, and then you got to clean your substrate. So, substrates are basically cleaned to remove the organic residues such as skin oils, inorganic contaminants such as dust, metal particles and the absorbed moisture. So, the common methods include something like solvent cleaning. So, you can use solvents like acetone, isopropyl alcohol and methanol in ultrasonic bath to dislodge the contaminants. You can also go for piranha solution, that is a highly corrosive mixture of sulfuric acid and hydrogen peroxide that can be used for removing stubborn organic residue, and this is an extremely hazardous process. You can also think of plasma cleaning by exposing the substrate to an oxygen or argon plasma to ionize and remove the atomic level contaminants. Now, in the substrate preparation steps, the fourth one is rinsing and drying. So, after you are done with the cleaning, the substrate must be rinsed with deionized water and thoroughly dried to prevent water spots and ensure good adhesion to the subsequent layers, and this is basically done using nitrogen or air gun. Substrate treatment is then done using oxygen plasma or UV ozone cleaning for organic removal and surface activation. You can apply adhesion promoters such as HMDS, which is hexamethyl disilazine, Okay, this may be applied if the photoresist is going to be used later, and then finally you do polishing or planarization based on your requirement. So, if you want to go for high quality nanofabrication, that is in optical and terahertz regime, so you need to ensure that the surface roughness is below few nanometer of the root mean square value. Okay. So, chemical mechanical polishing may be then applied for silicon glass wafers, and finally you can do the drying, that means bake the substrate at a temperature of 100 to 150 centigrade for 5 to 10 minutes. That will help you remove the moisture content. And finally, you inspect your substrate under microscope for particles, scratches and cracks before you move on to the next step. So, once prepared, the substrates are also typically stored in a clean dust free container such as a nitrogen purged desiccator or a clean room storage cabinet to prevent recontamination before you can actually begin your fabrication steps. So, now let us look into the first method of depositing the thin films. Okay. So, thin film science is a broad field used in various industries. They basically serve different purposes. They can be used for reducing reflections, preventing damage or altering properties, right. So, an important application is the gate dielectric in transistors which are often less than 10 nanometer thickness. So, as you can understand, these films can be really thin, starting from 10 to 1000 of nanometers for visible and infrared light. And if you go for extreme UV light, the films will be even more thinner. So, that will be only 1 to 2 nanometers, which are typically used in photomasks. Okay. So, thin film properties change based on how they are made. So, the key properties basically include how well they coat the surface, their density and their electrical behavior. So, here you can see one such example of thin film. So, here is the substrate and this is the thin film B that is deposited on the substrate A. Now, the density is important because it affects how light bends in the film, and stress can wrap or crack your film. Okay. Impurities, grain size and how tightly the particles are packed, they all affect how well the film is going to conduct electricity. So, its electrical behavior, the density also tells about the stability of the film. Now, let us look into the deposition methods of making these thin films. So, thin films can be made in two methods, which two buckets you can think of: physical methods and chemical methods. Now, physical methods basically involve transferring the material from the source to the substrate without changing its chemical state. So, two commonly used methods for making thin films or adding thin coatings are basically evaporation and sputtering. So, these methods basically work like a special kind of painting with vaporized materials by adding tiny particles to a substrate. Evaporation and sputtering are a part of a group called physical vapor deposition. So, in PVD, that is a popular name for physical vapor deposition, the materials are basically transformed into vapor and then layered onto a substrate one atom at a time. These processes are often carried out in high vacuum chambers that could prevent interference from gases in the surrounding. Whereas in the chemical methods, you will see that the film is basically created as a byproduct of some chemical reaction. Now, evaporation will involve heating the source material a lot until that converts into vapor, right. So, vapor pressure becomes a key parameter here, and all materials evaporate at a specific temperature. As you can see here, mercury, gold, all these different platinum. I will not read out all of them, but this is the vapor pressure axis and this is the temperature axis. So, it tells you that common materials will barely evaporate at room temperature because the temperature here are very high. Okay, and for something like gold, if you can see that if you have vapor pressure or the temperature If you change the temperature to 1500, then the vapor pressure is something around 100 millitorr. Okay. So, vapor pressure also depends on the position in the vapor stream. So, the pressure basically decreases as the vapor moves away from the source. So, to calculate the film growth rate, the pressure connects to the rate of atoms hitting the surface. So, often instead of directly measuring the temperature and the vapor pressure, deposition rate is controlled by adjusting the power to the source. So, here we will see one example of resistively heating evaporation method. Okay. So, there are basically two types of evaporation methods based on how power is basically given to the source. So, in one case you can see the pellets of the source material are basically put in a metallic container, okay, or something like a boat, okay, and that is heated using a strong electric current, something around 100 amperes. Okay, it will heat up and you are getting basically resistively heated evaporation. So, it is simple, and these vaporized molecules will go and deposit on the substrate in this vacuum chamber. So, it is simple, it is needed only a low voltage DC source, but it has got some drawback like inefficiency and potential contamination due to other parts also getting heated up and getting evaporated along with the source, right. The second method is called electron beam heating. So, you can see there is an electron gun that is giving these heated electrons which are accelerated through this high voltage, that is around 10 kV, and they are focused only on the source pellet. So, you basically use a magnet to redirect the beam so that they can go and heat the pellets. So, this also happens in vacuum. So, the electrons can be controlled using magnetic field without hitting the gas molecules, as you can see here. So, electron beam is basically efficient, they are accurately heating the source and minimizing the contamination, but as you can see it requires a complex high voltage power source. And safety issue becomes important because you are using very high voltage source. So, despite this, this is called electron beam evaporation. This is a widely used method in thin film R&D, right. The other method is called sputtering. Now, sputtering deposition basically uses a vacuum system with an excited gas plasma. Okay, so, plasma ions are basically directed at the cathode, as you can see, knocking the neutral atoms off the surface, okay, and all these atoms will collect on the substrate here, okay, and it will form a thin film. So, unlike evaporation, sputtering basically does not rely on heat. Here the atoms are basically ejected by momentum. So, that leads to denser films. So, in sputtering, the target material is basically bombarded by energized ion, which is typically argon plus, as you can see, and they are ejecting the materials that will be essentially deposited onto the substrate. So, you will get the film growth here. So, the target temperature basically rise is much lower as compared to the evaporation, because sputtering is basically a momentum transfer process, not a thermal evaporation. And sputtering can happen upward, downward or sideways, while evaporation can only happen upward. Okay. Now, the targets and the plasma sources in the sputtering can be made of different shapes for various coating setups, such as circles, rectangles or even unusual shape. And the plasma power in the sputtering comes from either a DC or a RF source. So, if you work with metal targets, DC works well, and if you are going for insulating targets, you have to choose the RF source, where the target basically acts like a capacitor for the plasma. So, thus you can see that sputtering is better suited for thermally sensitive compounds such as oxides, TiO2, zinc oxide or Al2O3 alumina, and nitrates, aluminum nitrate and titanium nitrate. okay, because the targets basically remain at relatively low temperature compared to the evaporation, and that basically reduces the risk of thermal decomposition, or you can say a stoichiometric imbalance. Now, in sputtering, you can see that the atoms might collide, okay, among themselves before reaching the substrate, okay, due to the plasma gas, and that makes it less directional than evaporation. Okay. Now, reactive sputtering is a variation where a bit of reactive gas like oxygen or nitrogen mixes with argon to create compounds from ejected target material, right. So, during this process, atoms are ejected from the target by energized ions to form a plasma that is basically directed to the substrate under very high vacuum. Okay. So, this is your vacuum chamber, this is the target, this is the substrate, and here you have these different gases coming in. Okay. So, normally argon is the commonly used sputtering gas, and the sputtering is carried out with DC power source, okay, or you can also use RF alternating current or ion assisted deposition. Now, in the case of reactive sputtering, a reactive gas such as oxygen, if you want oxides, or if you can allow nitrogen if you want nitrates, that is also passed to the reaction chamber along with the argon. So, these reactive gases basically react with the target atoms in the plasma to form the desired composition, and then it get deposited, right. So, while forming peroxide oxide films, multiple targets with different elements are simultaneously sputtered. So, they are basically reacted with oxygen and deposited as a desired film. So, since the target elements and oxygen exhibit a large electronegativity difference, the formed ions you will see can basically have negatively charged, and they are accelerated towards the substrate due to the difference in the potential of the negatively charged target and the grounded substrate, right. So, here this is the target and this is the substrate, right, and these ionic fluxes possibly act as sputtering ions to resputter the growing thin film on the substrate or modify the composition of the films or basically etching the substrate. Another method is the pulsed laser deposition. So, PLD basically employs brief powerful laser pulses, typically a few nanoseconds one, to remove the target material. So, here you can see laser energy is basically focused on the target substrate that causes rapid material evaporation and atom ejection. So, you can see a plasma plume here, and these atoms are basically then gathered on the substrate. So, a key advantage in this pulsed layer deposition is that you can perform this under ultra high vacuum or with various pressures or gases due to the laser source being external to the vacuum chamber. And the main advantage of PLD is its non-discriminatory nature and ability to remove target material in a stoichiometric manner, treating all atoms equally due to high laser fluence and rapid ablation. So, PLD is basically particularly suited for complex ceramic films like YbCO, yttrium barium copper oxide, lead zirconate titanate PZT, and various kind of carbides, oxide and nitrides. They are typically challenging to deposit from other methods. So, now let us look into the chemical methods. Okay. So, the chemical methods offer uniform, well covered and stoichiometric films, but different gases and chambers are often needed for each type of the film. So, the most common chemical method is the chemical vapor deposition CVD, where gas precursors basically enters the chamber and a high substrate temperature prompts the reaction okay, to create the desired film. There are different types of CVDs. One is called low pressure CVD, LPCVD, atmospheric pressure CVD, plasma enhanced CVD, and atomic layer deposition. So, CVD basically requires low pressure and high substrate temperature that ensures that reaction occurs only on the substrate surface, not in the gas phase, which could lead to particle formation and surface deposition. So, here is a setup for low pressure CVD. So, this reactor consists of a quartz tube connected to a pump. Okay. The gas inlet is basically used to introduce the reactant gases as well as the gases used to purge the system, such as nitrogen. Now, the wafers are loaded through the door on the left. So, this is the load door. In a low pressure system, the wafers are placed closer, as you can see here. Okay. A furnace basically encompasses your quartz tube. Okay. This is the quartz tube that is encompassed by a furnace. So, this basically heats the chamber, driving the reaction rate faster, and the advantages for low pressure CVD includes a relatively simple design, excellent economy, high throughput, and good uniformity. However, the disadvantages of these systems will include some susceptibility to particle contamination, which necessitates frequent cleaning and the need to compensate for the gas depletion effects. Now, this is plasma enhanced CVD. So, single wafer process chambers for plasma enhanced CVD look somewhat similar to that of the low pressure CVD. Okay. So, here you have the inert gas and the process gas inlet, you have the RF power. Okay. This is the wafer, and then it is on a heated plate. Okay. So, it basically tells you the single wafer plasma chamber, and this is the byproducts coming out. Okay. So, as with the single wafer LPCVD chamber, you can see that the precursor gas is basically fed to the chamber using the shower head arrangement, okay, to ensure uniformity of the precursor concentration over the wafer face. So, this is where the wafer will be lying. Now, direct exposure radio frequency PECVD systems typically employ the shower head as an electrode for introducing the RF power or the RF energy to create the plasma. Now, the precursor entering the plasma undergoes these electron molecule collisions, producing high energy excited molecules and molecular fragments that absorb the substrate surface, that basically absorb on the substrate surface and deposit the film. So, here you can see that like LPCVD, the wafer basically sits on a heated plate, okay, and the byproduct gases are basically exhausted through the ports below the wafer level, and this is a rotating system like before. And the final method we will be discussing today is the atomic layer deposition. So, this ALD process basically starts by a pulse of metal organic precursor gas into the deposition chamber. Under certain conditions, the gas basically reacts with the surface species of the substrate in a self-limiting reaction that is terminated when the surface runs out of the reactants, right. And the excess gas is then purged in the second stage with a neutral gas, something like nitrogen or argon, based on the process requirement. Okay. Then the second reactant is basically introduced in the chamber in the third step. So, here again it reacts with the surface species, and the excess reactant and the products are again purged in the fourth step, okay, concluding one particular cycle, and this goes on. So, in an ideal atomic layer deposition process, one atomic layer of material is basically deposited, okay, in every cycle, and the number of cycles basically determines the thickness of the deposited film, and you are doing it atomic layer by layer. So, with that we conclude our lecture. So, if you have got any queries regarding this lecture, you can drop an email to this email address. Thank you.